Hello, welcome back. So let's continue with multidimensional sampling. In one dimensions, as we said last time, so you have signal x of t, and to convert it into a signal x of nts, so to go from continuous time to discrete time, where n is an integer and ts is a positive parameter. So basically here we take the values of the signal on a uniform grid or uniform lattice, in which the separation between two points is basically equal to this parameter ts, which we can call the sampling interval. So we can model this by saying that x of t is multiplied by a train of Dirac deltas that looks like this. Now, in multiple dimensions, what is the equivalent of the train of Dirac deltas? Well, things are complicated if you have 2 dimensions or more. So basically, there will be a pattern for the Dirac deltas, and this will be characterized by a periodicity matrix Q. So Q is a periodicity matrix. It is invertible, and it tells you basically what is the pattern of your sampling. And so now we have T. So T, of course, is now to be understood as a vector T1 to Tn, n dimensions, and V is a vector of integers in the n-dimensional space, and Q is an invertible n by n matrix. So the most simple type of sampling in multiple dimensions, and like to visualize things, let's have it in 2 dimensions. So if you have just T1 and T2, basically to have a rectangular grid, which means that you sample basically the locations of the Dirac deltas basically are those points that are arranged on a rectangular lattice. Okay, and so the Q matrix, it is diagonal. It has 2 parameters, 2 positive parameters, Tx and Ty, and Tx gives you the sampling interval along the T1 direction, and Ty gives you the sampling interval along the T2 direction. Okay, so this is like, if I tell you, just suggest a sampling pattern, this is what you will come up with, and you can basically generalize this to n dimensions. The corresponding Q matrix will be basically a diagonal matrix with positive entries along the main diagonal, and those entries will give you the spacing between 2 consecutive samples along one of the axes. But you do not need to do this. Okay, so you can have sampling pattern basically that looks like this. Okay, so here your Q matrix, again, if you look at the columns, so there is Tx0, okay, and there is another vector which is Ty. Okay, so now if you imagine that this is multiplied, if you take basically Q and multiply it by Z1, Z2, and those guys are basically living in, each one is an integer, so they are living in the 2-dimensional integer space. Then, for example, of course, you'll get the origin. You'll get the origin when you multiply by 0, 0. But if you start basically sweeping through the values of the first component here and the second component, you will get a pattern of sampling. So those are like the quote-unquote the locations or positions of the Dirac deltas that look like this. Okay, so you move with a distance Tx. So Tx0 here means that this separation here is Tx, but then, in the y direction. So if you have a point here, to go to the next point, you will basically have to move Ty here and Ty there. Okay, so so again, like you take this matrix, you multiply it by an integer vector, or a vector of 2 integers, then you will generate basically this pattern, and of course it extends to infinity in all directions, and it is also a valid sampling pattern. And shortly in the lecture, we will see, what can be an advantage of doing something like this, or let's put it more accurately, what is the advantage of deviating from this thing? Right? This thing like seems straightforward and intuitive. It's like you just sample along each axis with a certain spacing. why do something, that seems like a bit complicated like this? But anyways, what you need is just a periodicity matrix that is invertible, so it has n linearly independent columns, and in one dimensions, again, if we go back, I mean, it's always good like to revisit the one dimension to understand what is going on. So in one dimension, you take a sample every Ts, and so there is the famous parameter Fs, the sampling rate, which is the reciprocal of Ts. So if you take a sample every Ts units of time, then in 1 second, say, you collect Fs samples. So that's the density of sample. Okay, so Fs, which is 1 over Ts. Okay, and as Fs gets larger, basically you are collecting more samples. And so it means that like you have more storage requirements. You are basically burdening your digital signal processor because you will have to deal with a larger number of samples per second. Okay, so increasing Fs is sort of good in terms of getting a signal that is as close as you wish to the original continuous time signal. But again, think about this big problem, which is an increased number of samples per unit time means, again, this will put a burden on your transmission. So sometimes you take this signal, like when you talk, on the phone or something. Basically, your voice is a continuous time signal. It is picked up by a microphone. It is basically sampled using an analog to digital converter, and then it is transmitted. So if you have more, if the number of samples per unit time increases, then again you are putting more burden on the communication system, on storage, if you basically take these samples and then store them, and so on. Okay, so in multiple dimensions, so what is basically what is the thing that is like 1 over Ts in multiple dimensions? It is the 1 over the absolute value of the determinant of Q. Okay. Okay, and this reason is like what I said in the previous lecture. Basically, the absolute determinant is the volume of the the fundamental polytope, parallelotope or parallelepiped, and so basically you take a sample every fundamental set. Okay, so basically it's 1 over the absolute determinant. Okay, so in one dimension, how do you understand sampling? I mean, remember the Nyquist rate and so on. How do we know the Nyquist rate? So the idea is that you take a signal and then it's sampled, and then you ask yourself, okay, so in the time domain we are basically picking the values of the signal at the integer multiples of this parameter Ts. But it's not clear exactly what is going on. And so let's basically take the Fourier transform. So in one dimension, the idea is that you write down, this summation n minus Ts, and then you apply the properties of the Dirac delta and say that this is summation x of n Ts delta n minus Ts. And then the trick is to take the Fourier transform of both sides. And since these are equal mathematically, then the Fourier transforms are equal. And so the Fourier transform of this thing will be basically the Fourier transform of x of t convolved with the Fourier transform of the train of Dirac deltas. And this will be equal to, take the Fourier transform here, assuming that you can take it term by term. And so the Fourier transform here will give you e to the minus pi 2 pi f n ts. Okay, and so this is actually by definition the Dtft of the discrete time signal x of nts, and this thing is what gives you insights about what's going on, because once you do the convolution, the CTFT of a train of Dirac deltas, as we did last time, is a train of Dirac deltas, and so this will give you fs summation x of f minus nfs. So basically, the spectrum of the signal is periodized. Okay, so sampling, the sampled signal, its spectrum is periodized, and I emphasized in the previous lecture, this issue that the Dtft by definition is a periodic signal. And so if you have a continuous time signal that you sample, basically it's a spectrum, it's a Dtft is a periodization of the original spectrum. Okay, so the spectrum of the original continuous time signal, it is periodized, and by periodized it means that it is shifted at all integer multiples of fs, and then you have a summation. And of course, this thing may blow, but let's assume that we are talking about some nice signal for which this summation here is finite for every frequency, and then you have this scaling factor fs. Okay, so when you discretize, basically in one domain, you induce periodicity in the other domain. So basically, once you sample in time, you convert the signal into discrete. Then your spectrum, the CTFT of x of t now becomes a Dtft, and it is periodic, and it has this specific form. It is the original CTFT, but now it is shifted at all integer multiples of the sampling rate, and then it is added, and then it's multiplied by the scaling factor fs. And from that we basically got to this idea of, so what is the minimum sampling rate so that you avoid aliasing. Okay, so but before revisiting this, let's actually do the same for a multidimensional signal. Okay, so any questions? So the next step is basically I will repeat this for a multidimensional signal. So again, you have you have x of t, and you have x of t. It is now multiplied by the train of Dirac deltas, but those guys now, so t here is again is an n-dimensional vector. We have functions of n variables, and this is minus qv. And this thing here can be written also by the properties of the Dirac deltas, that it is basically x sampled every qv, and then we have delta t minus q. Okay, and then you can take the CTFT of both sides, assuming that CTFT is an integral, assuming that you can interchange the order of integration and infinite summation. Then basically this guy here, when you do the CTFT, this is x qv, but then you take the CTFT of the Dirac delta, so that's the shift. So this will be e to the minus I 2 pi f transpose qv. What will happen on the other side? So on the other side we have a product, okay, and so by the convolution theorem, this product becomes a convolution. So you have the CTFT of x of t, let's denote it by x of f, and then product becomes a convolution, and then the CTFT of basically the Dirac delta is basically also Dirac Dirac deltas, but they are characterized by the matrix q minus inverse transpose. Okay, so basically this thing here, if you take its Fourier transform, it basically gives you this, and then summation x of f minus q inverse transpose k. So k is, so basically we have n sums actually. So we have n sums. Okay, so this thing here, it's a shorthand for summation k1 in z, k2 in z, up to kn in z. Okay, so we have basically n summations, and now this, so like in one dimension, if the Dirac deltas are spaced by ts in the time domain, they are spaced by 1 over ts in the frequency domain. So the generalization of this is that if you have a periodicity matrix Q, okay, then the Fourier transform, the periodicity matrix will be Q inverse transpose. Okay, and it's, I write it like this. I mean, you can write it like Q inverse transpose. It is this one or it is this one, because you can prove that if you have an invertible matrix, so if you invert the matrix and then transpose, it is exactly the same if you transpose the matrix and then take the inverse. Okay, so sometimes I just write it as Q inverse transpose because it doesn't really matter which order you do these two operations. Okay, and then by the properties of, again, of the, okay, so this is delta, convolution with the delta, again, it's like in the one dimension, it's basically you rewrite the summation here with delta replaced by x. Okay, so this is what you get. Okay, in one dimension, again, to put things in perspective, would be nice actually to have the one-dimensional result here. So the one-dimensional result here is fs summation k in z x of f minus k fs. Okay, so fs is 1 over ts. So it's like this 1 over absolute determinant, and the other hand is basically x of n ts. Okay, e to the minus I 2 pi f. Okay, so let me write it actually with v like this one. So v now is an integer, so vts, and this is f tsv. Okay, so that you can have basically the two forms, you know. So this is the this is the generalization of this. And again, in one dimension, I mean, if you want to do uniform sampling, okay, so non-uniform sampling is another business, okay, and you will encounter it in a couple of homework problems in which, like, you can sample not like on a grid, not on a lattice, but for uniform sampling in one dimension, you know, you just need to specify the spacing between two consecutive samples. That's it. You know, there is nothing more mysterious. In two and more dimensions, you will have to specify the periodicity matrix Q. Okay, and this result, you know, in multiple dimensions, it tells you that also what happens is that if you sample a multidimensional signal, basically it's CTFT. Now it becomes a discrete time signal, and its Dtft is basically the CTFT periodized. Okay, so it's basically repeated now. So you repeat it by the matrix Q inverse transpose. Okay, so it's the same idea. You know, the same idea, and we will, to have a feeling, we'll like look at, you know, specific example in 2 dimensions, because like it's easy to visualize things in 2 dimensions. Okay, so this thing in 1 dimension is the Poisson summation formula, and this will be the multidimensional. This will be the multidimensional Poisson summation formula, and again, it's a very nice result on its own, and you know, you can use it to compute DTFTs. Okay, so Poisson summation formula, because like one side, whether in the 1 dimension or the n dimensional case, one side is the DTFT. So you can use the Poisson summation formula to compute DTFTs. Okay, especially, you know, if you have if you have a summation that looks like tricky and not, you know, that you cannot manage, because like in many situations, yes, you have infinite sums on the right hand side and left hand side, but sometimes basically, you know, these sums here are very manageable. Okay, and so you can have like a DTFT that looks very complicated, but by employing the Poisson summation formula, you write down things using this other sum, and you find that you get like a nice, sometimes closed form result. Okay, so that's the multidimensional Poisson summation formula. And again, this side will be the DTFT of the discrete time signal. Okay, so the spectrum is periodized. Okay, and now in the frequency domain, the periodicity matrix is Q inverse transpose. Okay, so basically, what is Q inverse transpose? If Q itself is, you are doing rectangular sampling. So that's, the simple case. So if you are doing rectangular sampling, which means that in the time domain, and again, I'm using time not really to mean time, right? I'm using time, as a generic name for basically those dimensions. For an image, so an image is an example of a 2-dimensional signal. Basically, those will be spatial dimensions, x and y, right? So again, t, do not take it like, it's time literally. Okay, so sometimes it's time, but like if you have a multidimensional signal, a video signal is a signal with 3 dimensions, with one time dimension, and the other 2 are spatial dimensions, right? But like we don't have like t1, t2, we don't have multiple time dimensions. But again, the use here of time is just a name. To like generalize things from one dimension, do not take it literally. So if your Q matrix is diagonal, so again, like in time, what you do is basically you sample over a rectangular grid, and you have a spacing that is basically parameterized. So you take, so let's have sample. So along the direction t1, the spacing here is tx. And along the direction t2, the spacing here between these 2 consecutive guys is ty. And what is Q inverse transpose? Q inverse transpose, again, you can just compute it. It is 1 over tx, 1 over ty. So what does this mean? It means that the original CTFT of a signal that is sampled using this Q matrix, the spectrum will repeat itself, or will be periodized. You will have replicas, aliases, and they will be centered. Okay, so assume that the original signal has a spectrum that is centered around the origin of the frequency domain, Now you will have replicas centered at all those points, or that you see here, this grid, in which the spacing is 1 over Tx along F1 and 1 over Ty along F2. Okay, so you have a signal, and then it will be periodized, and again, if the signal is baseband and it's around 0, 0, then it appears around 0, 0. It appears around 0 and 1 over Tx, 1 over Ty. It appears about 1 over Tx and 0. It appears about around 1 over Tx and 1 over Ty. It basically appears, take this matrix and multiply it by any two-dimensional integer vector, and you will get, so it will basically be repeated in the two-dimensional space. Okay, so that's the sort of the effect of sampling, which again is like in one dimension, right? So in one dimension, you start with a signal that that becomes periodized when you basically sample it. And now, if you start with this Q matrix, which is not rectangular, of course, I mean, so basically this matrix, it's plotted on the previous page, and then the pattern of repetition in the frequency domain again is characterized by Q inverse transpose. And so you can get Q inverse, then transpose. This is Q inverse transpose. And so basically, the pattern, your original spectrum will be repeated about all of these points. And definitely, if your signal is not band limited, then all those replicas will overlap. The overlaps does not necessarily mean that basically the sum, the periodization, will explode to infinity. Okay, it may also, it may be finite, and this is actually the assumption that when you periodize, we are dealing with signals in which the periodization is finite for every frequency. But the idea is that there will be overlaps, there will be aliasing if your signal is not band limited. Because if your original signal, its spectrum is basically is defined over the whole F1, F2 plane. If it's a two-dimensional signal, then if you shift it, well, I mean the shift will overlap, with the original signal. Okay, so this is like again, it's the same story in one dimension. Right? In one dimension, if I have suppose that this is the CTFT, of x of t. Now, if you basically periodize this thing, okay, so you take this and this and this, so it becomes repeated every integer multiple of fs, and then when you sum those guys, there will be overlaps. Okay, so we typically focus on band-limited signals, and the band-limited signals are a mathematical fiction. They do not really exist in reality, but we can get very close to band-limited signals, and actually we force our signals to be band-limited. So basically, in applications, what we can do is that you have a signal, and you can basically apply a filtering operation to the signal, specifically a low-pass filter, so that you force it to be band-limited. But you remove part of the signal, and which part to remove? Well, I mean, it depends. So basically, by removing the part of the signal, you are saying that in my application, those frequency components are not really important, and so we can just get rid of them. So we force signals. So typically we force signals to be band limited. Okay. Band limited is like mathematically is like a very strict concept. Okay. So a band limited signal will have like a definition like this. A signal is band limited. Okay, a signal is band limited. Now, there must exist. So let's talk about baseband signal. So there must exist some positive parameter p such that the CTFT is exactly zero. Outside the L2 ball of radius b. Okay, so basically the spectrum of the signal, the continuous time Fourier transform is non-zero. Is non-zero for frequencies around about 0, right? But there should be some number. If the L2 norm of the frequency vector exceeds b, then the spectrum, the CTFT, is exactly equal to 0. Okay, so in one dimensions, like this is a band limited signal. So from minus w to w, and this is exactly 0. It's a very strict definition. Okay, so you need to have 0. In practice, of course, like we don't have this. Basically, in practice, a signal is band limited if outside a certain range it is negligible. Okay, so this is basically what we have in practice. But mathematically, it is basically equal to 0. Okay, so this is an example. This is an example of a band-limited signal in 2 dimensions. So this is a signal, okay, and in 2 dimensions, it's a spectrum. Basically, is defined. So x of f1 and f2, or x of f, is basically non-zero over just this circle here with radius w. Outside, it is equal to outside is equal to 0. Okay, so that's an example of a band-limited signal with like sort of a circular spectrum. Okay. So again, like if you know what is the meaning of f1 and f2 and f3 and those frequency variables, go revisit basically the notes on 2-dimensional Fourier transform, because in those notes there is an explanation of what is the meaning of a 2-dimensional sinusoidal signal. Basically, Fourier analysis is a decomposition of the signal in terms of sinusoidal signals. Okay, and so basically to understand the frequency variables, you need to understand what is a sinusoidal signal. And in 2 dimensions, you need to understand what is a 2-dimensional sinusoidal signal, right? So it's characterized by 2 frequencies, right? Because you can imagine like it is basically like a wave like a C wave or something like this in 2 dimensions, and it needs actually 2 parameters to be, f1 and f2, 2 frequencies. There are 2 frequency variables. So again, if you can revisit this and read it carefully, or you can just take it for in an abstract way, in the sense that the Fourier transform is a transformation. So you have your function, it's defined in terms of t1 and t2. The Fourier transform is basically a machinery, or an operator. You feed it a function of 2 variables. It spits out a function of 2 other variables without being close attention to actually what is the meaning. You can just you go from a function here from R2 to C to another function R2 to C with those new variables that are called F1 and F2. It's up to you. Okay, it's up to you whether you want to understand these things like very in an abstract way, or you want like it have a meaning. If you're doing digital signal processing, it's better actually that you understand what is the meaning of these things. In this course, typically, because like we are doing things like in math way, and we don't really delve into applications and so on, you can just take it, it's Fourier transform is just an operation. Anyways, basically, so suppose that your signal is like this, and suppose that you so it's a band limited signal. Okay, so if you don't want anything, when you sample the signal, it will always happen that again the Dtft will be periodized. It will be repeated. It will be repeated everywhere in our case here 2-dimensional plane. But then you don't want those replicas to overlap. Okay, so that's basically the idea of the sampling theorem. Now, the periodization in 1 dimension is straightforward. Basically, the spectrum will be repeated every integer multiple of fs, which is 1 over ts. Now, the periodization here will depend on the Q matrix, right? So if your Q matrix is is rectangular, then Q inverse transpose is also rectangular, right? So so if you have a signal that looks like this and you want to avoid anything, one way of doing things is to say, okay, I will have my Q inverse transpose matrix that is diagonal, and the main diagonal elements are 2W. So again, why is this? So the idea here is that if this is Q inverse transpose, it means that your spectrum will repeat. Your spectrum will repeat along each axis every 2W. This is the meaning, So basically, that if you again multiply, take 2W 0, multiply it by vectors, an integer here and an integer there, and sweep through all possible values, you will generate a lattice, and this lattice, a rectangular, actually here is square lattice, in which points, basically are along the orthogonal f1 and f2 directions. They are separated by 2W. If the original spectrum looks like this, there is no aliasing, right? Because there, so basically if you have this, the spectrum is defined over this circle. Now, it will be repeated, but if you go away by 2W, then, so again, so there is a W here, and then there is a W in that direction, and the difference between the centers is 2W, so they will barely touch. Okay, and so this will be a case of no aliasing. So this is in 1 dimensions. If we go to 1 dimensions, remember, if you have, like, this is the signal, it will be periodized, and so this is 0, this is Fs, and then you ask yourself, what is basically Fs, so that we don't have aliasing? Then you say, okay, if the bandwidth is W, okay, so this is just, a replica of that one. So if this is centered at 0 and it goes here to W and here to minus W, then this Fs here, it will be Fs minus W, and this will be Fs plus W. And then the condition for no aliasing in 1 dimensions is say, okay, to avoid the overlap, I want this point to be above that point. Right, so if you reduce Fs, this replica will get closer to the origin, and then you have, the possibility that you have a spectral overlap, the so-called aliasing. But you say, okay, I will choose my Fs such that Fs minus W is greater than or equal to W, which means that I want this point to be greater than or equal to that point. And so, this is the, so Fs greater than or equal to W. 2W is the minimum, strictly speaking, you should be like even an infinitesimal quantity above 2W, but I mean, we will not like basically give attention to this detail. So same thing here, which is like, so your spectrum looks like, so basically your spectrum is something that is non-zero above this circle here. So again, your spectrum is a function x of f1, f2. So what I am drawing here is basically the support. Okay, and and I'm shading this part to tell you that basically x, to tell you that x of f1, comma f2 is non-zero, here. Okay, but it's zero out, it's zero outside because of it's a band limited signal. Now if you want, basically when you sample, this function will be periodized by the matrix Q inverse transpose. And we don't want the replicas to overlap. So the way to go, like, or it's one possibility. See, in multiple dimensions, we have more possibilities. In 1 dimension, it's like very clear. You don't have any other option. It's like, you are just in 1 dimension, and you say, well, no aliasing is if S is greater than or equal to 2W. Now you can do it this way. I say, okay, I will choose Q inverse transpose to be 2W, and 2W along the main diagonal 0, 0, which means that when the spectrum is periodized, it looks like this, so no overlaps. And like if you want to reconstruct back your signal, what do? Like in the 1 dimensional case, you do low pass filtering. Okay, so if you want basically to get your signal, the continuous time signal back, you will have a low pass filter that will basically extract the original continuous time Fourier transform, like this, and this is the in the time domain. So in the time domain, what is the corresponding Q matrix? So the corresponding Q matrix is 1 over 2W, 1 over 2W, right? So so basically this is like in 1 dimension we say that Fs min is equal to 2W, and so Ts max, so the maximum sampling interval, is 1 over 2W in 1 dimension. So basically this is what is going on here. And this means that you go in the time dimension here, I am putting W equals to 1. So basically you take a sample from your 2-dimensional signals along this lattice, this grid here, and the separation between 2 successive points is 1 over 2. It's generally 1 over 2 W. If W is 1, then every half, like, you basically take a sample. Okay, so if you know that your signal has this spectrum here, then you may use basically this sampling pattern, this Q matrix. This Q matrix will cause the CTFT to be periodized in such a way, and there is no aliasing. And so you can, in principle, you can reconstruct your continuous time signal by doing a filtering operation. You basically have a 2-dimensional filter that will focus basically around the origin and will extract the original CTFT, suppressing the aliases, suppressing all the other replicas. But you know, in 2 dimensions, you have like more degrees of freedom, and actually this will also be a feature of higher dimensional signals. So I can also choose a Q inverse transpose matrix that causes no aliasing, okay, but is different from basically this. Okay, so this is one. Okay, so this is this is basically one in which you don't have overlap. Okay, so this is hexagonal sampling. Okay, so you see that the pattern here will be repeated. So this is the original spectrum. Now it is repeated, and you can connect to the centers of those guys, and you will see that the centers are basically living on the vertices of a hexagon. Okay, so that's hexagonal sampling or hexagonal backing. Okay, so by doing this you avoid overlap. So, right. Basically, if your objective is to avoid overlap, you can do it in a number of ways, and this is one way of avoiding overlap. And again, you are able, like in principle, to have a low pass filter that will extract the original CTFT. You don't have overlap, so basically you do it is like perfect reconstruction. Of course, there is nothing perfect in reality, because of like you never just do sampling. You do sampling and quantization, and there are always like practical issues related to sampling and quantization. But you can reduce those bad effects as you wish. So in that case, what is Q inverse matrix? Well, it is this pattern here, the pattern of the those red dots. And you can, as I said in the previous lecture, basically when you have a periodicity pattern, there is no like unique periodicity matrix. You can write it down in a number of ways. So now you need just to choose the columns to be linearly independent. So you can write basically Q inverse transpose. You can write it in this way. Okay, so this is the so you say, well, it's like I go along this direction with 2W. Okay, and 0, so that's one vector, and the other vector will connect these two centers, and you can, because this angle is 60 degrees, it's 2W cosine 60, 2W sine 60. Okay, but you can describe this pattern using you just need two vectors that are linearly independent, which like geometrically in 2 dimensions mean that the two vectors should not point in the same direction. Okay, so now what is the corresponding? So how do you do the sampling in the time domain? So this is Q inverse transpose that tells you how the replicas appear in the frequency domain. So in the time domain, what should I do? In the time domain, you should use this Q matrix. So the Q matrix, and you get it from Q inverse transpose, and this is how you sample. This is how you sample in the time domain. So as you can see, you also see the hexagons, right? So you can see that there is a hexagons here, and this is the pattern in which like you sample your two-dimensional signal. And if you sample using this pattern, I can compare like this one. This one is like the straightforward one, which like it comes to your mind. It's basically you do sampling with a certain interval along each axis. Okay. Here things are like a bit complicated, like so here you take this sample, so along this line there is a certain spacing, but then you do a shift like this. Okay, so this sampling again will result in this spectrum. And your objection will be, I mean, this seems like a bit difficult relative, at least to this guy, to do in practice. And so why the fuss? I mean, why should I be interested in using this Q matrix here, using a two-dimensional sampler that has Dirac deltas at those x's, rather than this thing here? It is a story. Again, like if you have a band-limited signal, again, like in 1 dimension, there is hope that you can reconstruct your signal. Okay, so this is again a result for all signals, 1 dimension or more. But you need to avoid aliasing. Okay, so that's the essence of the sampling theorem that you have studied in a previous course: signals and systems, digital signal processing, digital communications, whatever. So the idea is that you can reconstruct your signal so long as you sample it basically in such a way that you avoid aliasing. and in one dimension, so like fs is greater than 2w, which is like straightforward. Here, like things are difficult, and you need actually to look at the shape of the spectrum and so on. So here we focus on the shape in which like the spectrum has a circular support, and to avoid anything, you can do it in a number of ways. Now, mathematically speaking, you know, if you avoid aliasing, you can reconstruct your signal. Okay, so if you avoid aliasing, then your signal can be reconstructed. So what sampling better is better in that sense? Okay. Well, that's a complicated question because, like, you know, because there is the issue of complexity. Okay. But let's ignore complexity for a while. Let's assume that, you know, that you are basically able, using current hardware, like, to do sampling any way you wish. So would you do the sampling like this or like that? Well, in both cases, you are able to recover your signal, to reconstruct your signal. So a better sampling scheme will be a scheme in which you have a smaller number of samples per volume, and like in 2 dimensions, this will be per area, right? So you are taking samples here in this 2 dimension. So it's a signal that is defined in 2 dimensions, right? So how many samples do you take per area? Okay, so this is a very important parameter, because if I can reconstruct my signal using a fewer number of samples, then that's better. Again, because more samples is problematic in the sense that more samples means more storage, means more basically processing. If you are processing, typically you take those samples, quantize them, and then you filter them, you do many things to them. And so the more you have, then the more operations that you need to do. And if you transmit those samples, then you are basically putting stress on your communication system if you have more samples than needed. Okay, so now if you compare, the idea is, you know, this seemingly complicated better, it has an advantage because in the time domain, the density is smaller. So you are able to do perfect reconstruction, but with a smaller number of samples per area or per volume. I mean, as I said in the previous lecture, I will say per volume, but this is basically length in 1 dimension, area in 2 dimensions, and volume in higher dimensions. Okay. So in terms of sampling density, hexagonal sampling or hexagonal backing, you know, basically the density that, you know, this formula, and basically the sampling here. How many samples per unit volume or area? You can say area here because you have 2 dimensions. It's okay. It's 2 square root 3w squared. Rectangular backing here is like 2w. It's like what you do in 1 dimension and you square it. So it's 2, you know, because like you have 1 over 2w along T1 and 1 over 2w along T2. So basically it is like the result of 1 dimensions squared. So it's 2w squared. So it's 4w squared samples per unit volume or area. But if you go for hexagonal sampling, you can reduce this 4 to 3.46. Okay, let's say 3.5. So you go from 4 to 3.5. So 0.5 over 4. So you have a reduction of 1/8. Again, this may be significant. Okay, so these things are, you know, these things are important. In multiple dimensions, you have freedom. You know, how to avoid anything in multiple dimensions is not like in 1 dimension. 1 dimension, you know, I mean, you are stuck along the line. I mean, to avoid anything, I mean, you just need this replica to be far from that one. In multiple dimensions, well, you don't want overlap, that's fine, but you can do so in a number of ways. Okay, and so I mean, so the story becomes more interesting. Okay, so that's the business of multidimensional sampling, and you know, so we discussed multidimensional Fourier series, multidimensional Fourier transform, multidimensional Poisson summation formula, multidimensional sampling. So this is basically a generalization of what you have learned, telling you that, you know, multiple dimensions, basically, you know, the story. There are aspects that are the same, but there are like new things here. And one of the things is basically that periodicity now requires that you have this thing called the periodicity matrix. Okay, so any questions? As usual, I have said this before, but I will repeat it again. Like, if I ask you like something like related to multidimensional Fourier series, multidimensional Fourier Transform, and so on, or any other topic, typically the level of mathematical rigor in your solutions in the homework is basically the level that I use in the lecture. So, like in this lecture and the previous lecture, for example, like I liberally interchanged integrals and infinite sums, right? I say, okay, assume that we can do the interchange, right? So I give you a problem, you do the same. Okay, but in other topics, I will be like very, I will, for example, I want to show that something actually has a limit, the limit exists, and then I will show it, exactly by taking limit infimum, limit supremum, and so on. So you do the same. Okay, so you don't need like to ask me, so can I do this or that? Well, it depends on what I do in the lectures. So, I will not like do something here in a non-rigorous way and then ask you to do something that is rigorous. Okay, so you just follow. If I'm doing things, if I liberally interchange in this topic, then you do the same. Because like I think in homework 6, which is now on Blackboard, if you want to have a look, I will ask you like to prove Parseval's relation for the multidimensional Fourier series. Not a biggie. I mean, it's basically the proof is sort of like the proof I did for the coefficients in the previous lecture. Okay, and then I did this interchange. So go for it. Okay, no one like just do it. Okay, just do it. To do the Fourier series in a rigorous way, there is a framework, but this framework is very lengthy, and so we don't have time for it. Okay, so you can basically start by defining the Fourier series like sort of as an approximation with finite number of terms, and so by having a finite number of terms, you avoid these problems of interchanging order of integration and summation. Because if you have a finite sum, you can always interchange integral and the finite sum, because integral is a linear operator. So there is a way of doing this, and then you take limits, and then show that you are using a basis that is complete and so on. But again, we don't have time for this. So the level of rigor is what I'm doing here. Back to one dimensions, because as I said, like even in the course information, that this course like assumes that you know actually what CTFT, what DTFT. But what is Dft? Okay, so what is the Dft? And what is its efficient implementation, which is called the FFT. So the FFT is not a new transform or anything. It's called the fast Fourier transform, but it is actually a smart way to implement the Dft. So we need to understand now what is the Dft, and basically to understand things, you go back to the one-dimensional case. And then perhaps if we have time, we can go to the multidimensional case. Okay, so back to one-dimensional signals. And to start the topic of the Dft, we need to do two things to the Dtft. We need a window, and we need to sample the frequency variable. Okay, so let's see the story. So window Dtft. So you are a practical guy, and like again, like the signal processing is very practical, by the way. So even if the theoretical foundations can be very mathematical, but it is something that is designed basically to be implemented. So you are processing a signal, and so our signals in theory are those nonsensical signals that if they are continuous time, they are defined from t from minus infinity to infinity. And if they are discrete time, the index n goes from minus infinity to infinity. And so like, so in practice, it means like you will, you need like to start your experiment or your system like from negative eternity to collect your samples or do what? No, I mean, of course, this is, this is not something that you can do. So in practice, you will sample, you will use n samples, okay, and process them. So if sometimes you do this basically in a block by block basis. So you basically take n samples, and then you do some processing on them. Then you take another n samples and do some processing on them, and so on. So like a speech signal processing, for example, so again, you have many samples. You will not wait for all those samples and to start doing processing. It does not make any sense for actually a number of reasons. So what you do is that you take basically a block of n samples, and then you do something to this block of n samples, and then you take another block of n samples, and typically, to get good results, typically we do overlap. Okay, so you take another block of n samples. So this is another block of n samples, and then you take another block of n samples, and so on and so forth. But on a block you have n samples. You have a finite number of samples. Okay, so basically this is very important. That to be practical, I mean, you need to deal with a finite number of samples, and this is also important, because signals are in reality non-stationary. So their characteristics, their properties, they change over time. And so you want basically to process the signal over a duration of time, basically such that the signal over that duration of time is sort of has some fixed properties. So this is an assumption that's called quasi-stationarity. So for example, a speech signal, if you analyze it, the frequency contents of a speech signal over 10 milliseconds is sort of is stable, so you can do Fourier transform, but you should base it on a duration of 10 milliseconds, because after that it's sort of you have a new signal with new properties, and so on and so forth. So actual signals are typically non-stationary, and you basically divide your signal into blocks or segments of samples, and you do processing in a block by block basis. And again, you typically actually make the blocks overlap. So that's the idea of windowing. Windowing means that if you want to take the Dtft of a signal, so it's still Dtft, but I just want to take a summation from 0 to n minus 1. From minus infinity to infinity, that's nonsense. Okay, I will not wait infinity to basically to process my signal. It does not even make sense. I will get nonsensical results, given that actual signals also have properties that actually change dynamically with time. So you need to window your signal. So the first question that comes to mind is, well, so now what you compute now, the so-called window Dtft, is not the true Dtft. How is this Dtft related to the original Dtft, which is defined with the summation from minus infinity to infinity? So if you take a summation from 0 to n minus 1, it's like you take your signal multiplied by a window function, specifically by a rectangular window function. So basically it's as if you have, this is n, and you multiply your signal by basically samples of 1 from 0 to n minus 1, and then zeros otherwise. So you can write down this finite sum as an infinite sum, but now it's as if your signal is multiplied by a window, by a rectangular window specifically. So the windowed Dtft, it is like the mathematical Dtft that we know, but it's not applied to signal x itself, it's applied to signal x multiplied by a window. So do we get the spectrum of x? No, because we have a convolution theorem. So if you multiply two signals in the time domain, what you get is not, it's not the spectrum of one signal. You get the spectrum of the two signals convolved. Okay, and so basically what you get here is that you don't get actually the spectrum, the Dtft of x of nts. What you get is that spectrum convolved with the spectrum of the rectangular window, which is basically a discrete time signal that is one from 0 to big N minus 1 and 0 elsewhere. Okay, but it's an evil that we will have to tolerate because we cannot do otherwise. I cannot wait from minus infinity to infinity. Okay, but we need to understand what will happen. What will happen to your signal when you basically truncate it, when you window it, you segment it, you divide it into blocks, say whatever you want to say, okay? But this is, you divide it into frames. Some people call these frames. all these. But there is no way that you can do processing without basically doing this segmentation. And there is a price, and the price is that you compute the spectrum. Well, the spectrum that you get is not the true spectrum. So a complex sinusoidal signal, what is its spectrum? A complex sinusoid, if you study its Dtft, well, by definition, it is at frequency f0, so you should get a Dirac delta at f0, right? Because you basically are decomposing the signal in terms of the complex sinusoids, and so you get a Dirac delta at f0. And because we are talking here about the Dtft, so everything will be periodic, and so you get Dirac deltas at f0, f0 plus fs, f0 plus 2fs, f0 minus fs, and then there is a scaling factor fs. Okay, but this is what you get. Again, like in the continuous time Fourier transform, we don't have this periodicity, but we have the idea that if you have a truly sinusoidal signal at frequency fc, then you get a Dirac delta at fc. But now, what will happen if I take a complex sinusoid and I truncate it? I apply to it the window Dtft, which is like I take the signal multiplied by the rectangular window, and then I take the Dtft. Well, we can examine it. I mean, it's not a biggie. I mean, just write down the formula and see what you will get. So here is the summation. So here is your signal. Now you are picking the Dtft, and now you have a finite number of samples because you are a practical guy. You want to do practical stuff, and when in practice you cannot handle an infinite number of samples. You just need to operate on some finite number of samples. Okay, and so what is the window Dtft? Well, it's just a geometric series, and so you apply the rule of the geometric series, do some algebra, and this is what you get. So what you get is not the Dirac delta. You get something that's called the aliased. Some people call it the aliased sink. Some people call it the discrete time sink. Who knows what other names does this thing have? But it is sine over sine, and the difference between them. See, there is an n here, but there is no n there. Okay, and now if you plot the magnitude of this thing, of course it's not a Dirac delta. So again, like if you do the original Dtft, and you have a sinusoidal signal with a complex sinusoid with frequency f0, you should get Dirac delta at f0. But now what you get is this thing. You get something that it's like something that is trying to be a Dirac delta. Okay, and as you increase big N, basically the spectrum that you see in front of you will converge to basically to be a Dirac delta at f0, Dirac delta at f0 plus fs, a Dirac delta at f0 minus fs. But of course, n is finite. Okay, and so what you get, you get this aliased sink, or this discrete time sink. Again, any Dtft is periodic with the period fs, but just let's focus on this part around f0. Now, you don't get a Dirac delta, you don't get a sharp component at f0. You get something that is sort of a beak with a height n at f0, and then you have those annoying guys, and then of course again, mathematically speaking, the Dtft must repeat itself every fs. So basically, this is what you get if you take a complex sinusoid and you try to apply the window Dtft, which is like if you take the samples, multiply them by a rectangular window, and then take the Dtft, so that you do your operation using a finite number of samples. So there are two issues now. There are those annoying side loops. Okay, those annoying side loops. So basically, Dirac delta is nice, zeros. So basically zeros outside. Basically f0. But now you get values. So this is called the spectral leakage problem. So spectral leakage means that you get non-zero values for the Dtft, almost at all frequencies. The Dtft is zero now at those points only. Otherwise, the Dtft is a non-zero value. So this is called the spectral leakage problem. You want basically to get something at f0, but like you get non-zero components like sort of everywhere. and then you hope that basically this thing is concentrated about f0, but it comes with a width. So this thing is called the main lobe, and those are called side lobes. And so the main lobe, it has a width. Okay, again, you can go to the sign here and you examine. I mean, what when is this guy basically it will cross the 0, and basically the main lobe will be 0 at f0 plus fs over n, f0 minus fs over n. So basically the width, if you take half this width here, this is a famous parameter. Keep it in mind, because it's a very useful, and it's very, in practice, when we continue and study the Dft, this fs over n is like sort of a magical quantity. So fs over n. You increase n, this width will get smaller. That's good, but again, you cannot increase n as you wish, because there are practical constraints that are forcing you to adopt a certain n at maximum. So you have a spectral leakage problem. Spectral leakage, again, it means that you get a non-zero value. Where you should get 0 if you do the original Dtft. And then there is a resolution problem. And the resolution problem means that suppose that you have two signals at f1 and f2, and these are closed. Now what will happen if you apply the window Dtft? Now each one of those guys will be, one of those guys will be an aliased sink around f1, and the other will be an aliased sink around f2. And what you get will be something that looks like this. Okay, so basically that if these two guys are close, the main lobes will merge. And remember that in reality, when you obtain a signal that looks like this, it comes contaminated with noise. In the presence of noise, you will get something that looks like this. And you have no idea whether you have just one frequency component or actually two frequency components that look to you as if they are one, because they are very close to one another. So that's the resolution problem. So the resolution problem is, resolution means what? Resolution means the ability to distinguish between two close frequencies. Now the problem is that now each sinusoidal signal with a frequency f1 and f2, now it will not give you a Dirac delta. It will give you this aliased sink. It will give you this main lobe which has a width. And if the f1 and f2 are close enough, basically the superposition of the two components, if they are added together, you will get sort of like one main lobe. And in the presence of noise, it's very difficult to make, is this just one frequency component, or it is just two or three that are so close to one another? So this is the resolution problem. So basically, we have two problems. We have the spectral leakage problem, and the spectral leakage problem, again, if you want more details, again, if you like to have a more practical perspective, read the notes. So the notes on Dft, they give, there are examples telling you exactly what spectral leakage will cause you. So basically they may cause something called masking. Masking, which means that if you have two sinusoidal components and one of them in amplitude is much smaller than the other, the side lobes will make you unable to see this, the weak sinusoidal signal, the sinusoidal signal with a small amplitude. So again, go to the notes for example, but for us here, there are two issues: side lobes and the width of the main lobe. The width of the main lobe is causing a resolution problem. It will not allow you to resolve spectral components that are close to one another, and the side lobes they may actually lead you to miss some existing weak sinusoidal components. I mean by weak, with small amplitude. So it's a topic in digital signal processing, how to actually deal with both problems. Okay, so in this course we will focus on spectral leakage problem. So the spectral leakage problem, basically its solution is to use a window other than the rectangular window. Okay, so one solution is to say, perhaps, if we multiply by something other than this rectangular window, we can improve the performance. Okay, so this is basically the idea. For the resolution problem, there are techniques. There are things called super resolution techniques, but we will not deal with them in this course. Okay, our focus will be basically side lobe suppression. Side lobe suppression. So basically, target is if we have e to the I 2 pi f0 NTS, we want basically something that looks like this around f0, but with negligible side lobes. And of course, since there is no free lunch, if you want to suppress those side lobes, you always increase the width of the main lobe. So by basically solving the side lobe problem, we are making the resolution problem worse, because the main lobe will get fatter. But we don't care, okay? So in this course, we will assume that in our applications, the applications of interest to us are basically applications in which we are not really interested in resolution power, the resolving power, or to basically distinguish between close frequencies. We just want basically, if we have a sinusoidal component, we want, when we take the windowed Dtft, we want to have something that looks like this, not that looks like this. Okay, so the rectangular window will give you a main lobe that is narrower than this one, but it has those monster side lobes. Okay, so our objective is to sacrifice and make the main lobe wider, but kill off those guys. Okay, but like again, what if your issue is resolution? Well, then you will learn, you can take a digital signal processing course, learn about algorithms like, for example, music, multiple signal classification, and so on. Basically, algorithms that are dedicated to basically solve the issue of resolution. But for here, our topic will be the windows. Okay, so windows, in the notes also, you will find basically windows when people started like basically coming up with ideas for windows, there were like sort of engineering ideas, and so one of the first windows was called the Hamming window, and it is explained in the notes. Like again, if you want like to have more feeling about this, but here in the lectures I will just go directly to the so-called optimal window. Okay, so we'll basically try to like go directly for sort of a window with some sense of optimality. So this will be the Slepian window. David Slepian was a genius, and he did many things. This is just one of them, the Slepian window. And the Slepian window also, it has another name which is mentioned. It's called the discrete prolate spheroidal sequence. Okay, because it's actually related to to big problems that Slepian actually studied. Okay, but let's focus on our issue here. So we want a window whose spectrum. We want a window whose spectrum. Again, we don't like the rectangular window. The rectangular window, its side lobes are like high, such that in practical applications they cause you trouble. We want a window with side lobes that are small. Okay, so the window, again, to have a feeling of what's going on, so you take now x of t, you take x of NTS, and from minus infinity to infinity, you multiply by now a window, general window, w of n, NTS, okay, e to the minus I 2 pi f NTS. And to make this summation finite, okay, so the window must have, basically it is 0 outside and basically this set. So the window in the time domain is a window. Basically, it should basically make your summation with a finite number of terms. But the idea is that we will not insist that the samples of the window are all ones, like the rectangular window. Rectangular window is again equivalent to just truncating the DTFT, saying, okay, I will just do the terms from 0 to n minus 1. Again, the disadvantage of something like this is side lobes. Side lobes in the frequency domain. So in the frequency domain, you have something that should appear as a Dirac delta at f0. You get actually the DTFT of the rectangular window, which is this aliased sink, and around f0, and it has side lobes that are not acceptable in many practical applications. So we want to design a new window, okay, and basically given n, okay. So we will assume that you are a good engineer, and based on your application, you know what big N to use. So n will be the number of terms that you use for your DTFT, and you will specify a W. Okay, so you need to come up with a W, and this W is taken as a number between Fs over n. Again, Fs over n is not an arbitrary parameter. It is half the width of the main lobe if you use a rectangular window. Remember, the main lobe of a rectangular window. So if it's centered at f0, it goes from the main lobe goes from f0 minus Fs over n to f0 plus Fs over n. Okay, so again, this parameter is not arbitrary, and it's important to keep in mind. Fs over n. It turns out that it appears a lot in digital signal processing. So Fs over n less than W less than Fs over 2. Okay, so for discrete time signals, we Fs over 2 is like the highest frequency. So you come with n, you come with W, and so we want to design a window with a DTFT. Okay, so I will call the window Sn in the time domain, okay, and S for Slepian, and it has a DTFT. So we want the DTFT to be concentrated from minus W to W and negligible outside minus W to W, which is basically we want a main lobe. I mean, we will have to live with a main lobe, with a fat main lobe, but we want to suppress the side lobes. Okay, so the window, it has a DTFT, and what we will do is that we will maximize this ratio. So let's think about this ratio. So we want this, so magnitude S of F squared, so that's the DTFT of S of n, magnitude squared. We want this thing between minus W and W to be maximized relative to the total energy. Okay, so here in the denominator, we have an integral from minus Fs over 2 to Fs over 2, and you know this from your basically signals and systems course, that basically this thing here is the summation of the magnitude squared of the sample. That's the energy. So that's the total energy of the signal. Okay, that's the total energy. So that's the denominator. In the numerator, you say I want minus so the integral is from minus W to W. So you want this ratio to be maximized. And so what is this ratio? It's the ratio of the energy contained between minus W and W to the total energy between minus Fs over 2 to Fs over 2. You want this ratio to be maximized. You want basically, the spectrum outside minus W and W, that's the side lobes. You want those side lobes to be tiny, to be negligible. That's the idea. And again, rather than doing it in ad hoc fashion, like as you can see in the notes, the Hamming window and the Hamming window and so on, we want to do it in a principled fashion by setting up an optimization problem. And so this will be our optimization problem. Design the window that on the frequency interval from minus W to W, it has the maximum possible fraction of energy given two parameters. So there are two fixed things here. N, big N is fixed, W is fixed. Okay, so what are our optimization variables? The samples Okay, so the optimization variables are basically the samples of the Slepian window. Optimization variables are basically those guys, S of 0, S of 1, S of 2, up to Sn minus 1. Those are the guys that we want to obtain. You know, if the S's are actually all equal to 1, then we are talking about the rectangular window which has high side lobes that are problematic in many applications. We want, you know, so basically the solution will not be the rectangular window, it will be something else. And again, we will suppress the side lobes. And don't forget that when we suppress the side lobes, you will get a main lobe that is fatter than the rectangular window case. Okay, but again, there are some applications which side lobe suppression is the issue, and here is and this is our focus here. So our objective function alpha w is the fraction of total energy living in this interval. You can solve this problem in a number of ways, and one way, like if you write down things, basically I define this H vector. So H is a column vector of those guys. Those guys are, you know, the guys that appear in the definition of the Dtft. And then our optimization variables will be collected in the S vector, n-dimensional vector, and S0, S1 out to Sn minus 1. And what is S of f is the Dtft of the Slepian window. And let me actually write its formula. So it is the Slepian window again. It has non-zero samples only from small n, from 0 to big n minus 1. It's outside that is 0, and so it's Sn e to the minus I 2 pi fnts. Okay, and so let me actually write this as fts to the power n, right? So you can basically rewrite the Dtft as if it's H Hermitian. You take this Hermitian of the vector H multiplied by S, and this is exactly the summation for the Dtft. Okay, in the denominator of the Dtft by Parseval, again, this is something that you know from signals and systems, that basically this is the sum of the magnitude squared of the samples, and basically this is S transpose S. We are assuming that basically S will be real valued. So we want a window that is real valued. Okay, so you can write it Hermitian. It won't harm, but I mean, you know, I wrote it here transpose to emphasize that we want a real valued window. Now, so the denominator by Parseval is just S transpose S, which is the L to norm squared. So basically, this is the L to norm squared of vector S. What about the numerator? So the numerator is basically this here again. And so S of f is equal to H Hermitian of S magnitude squared. And so let's rewrite the numerator. Okay, so I will take H Hermitian S magnitude squared. So this is a scalar, the magnitude of a complex scalar squared. And I can write this thing here. Okay, so there is a Hermitian missing here. So this is, I can write it as H Hermitian S conjugate, H Hermitian S. And because this is a scalar, you know, conjugate is like Hermitian, and then this is S Hermitian, H Hermitian S. Okay, so you can write down this magnitude squared as a quadratic form, S Hermitian H Hermitian S. And where is the frequency variable? It's living inside H. Okay, so not a problem actually to reimagine what H is. H is this vector 1 e to the I 2 pi fts, e to the I 2 pi f2ts, up to, you know, basically this number becomes n minus 1. So basically the S's are just, you know, those S0, S1, Sn minus 1. Those are not a function of frequency or anything. Those are actually the time domain samples, and they are unknown. We want to actually solve the optimization problem so that we can get them. Okay, so we can take the S's outside the integral, and of course, I mean, this integration, it means it's an integration element by element, right? So I mean, you know, nothing fanciful is meant here. When I write an integration, and here we have a matrix, this is n by 1, this is 1 by n, so it's an n by n matrix. I mean that basically this is an integral that is applied to every single element in this n by n matrix. Okay, and so basically this integral of from minus 0 to w of H Hermitian, I will call it matrix, I will call it A, and so element Vk in matrix A is given by this quantity, right? So element Vk it means that, so this is the H vector, so there is some element here, VTS, and then there is a Hermitian, you multiply by its Hermitian, it's an outer product, and so there is an element here, e to the minus I 2 pi FKTS, and so element VK in the matrix will be that you take this one times this one, and you integrate from minus W to W and scale by 1 over Fs. So this will be element AVK, okay, in the matrix. Okay. Now we need to understand matrix A. So what matrix A is? What are its properties? So our optimization formula is basically to maximize this ratio here, which is the Rayleigh quotient. It's a Rayleigh quotient. We need just to understand matrix A, to have like a better feeling of what is going on. So the integral is doable. You can do it. It's an integration of exponential function, and you can express actually the elements of A in terms of the sinc function. Now this is good because now this is AVK. What about AKV? So AKV, you basically replace K and V, and the sinc function is an even function. So basically AVK is equal to AKV. If you basically switch V and K, you get the exact same value. And so it means that the matrix we are talking about here is a symmetric matrix, and that's good. That's good, right? Because symmetric matrices are normal matrices, and so they are diagonalizable, and and so on. So they have nice properties, okay? And they're, the eigenvectors can be like put in, you can have like an orthonormal eigenvectors and so on. So it is symmetric, okay? But there is something else. AVK depends on V minus K, depends on this difference. So this matrix is a tuplets matrix. Okay, so a tuplets matrix is a matrix, right? A tuplets, you may have seen it before, but if not, basically the elements on the matrix, basically, so on the main diagonal you have the same element, so A. So those are the elements whose the index differs by 0, and then here we have B, and then C. Got what I mean? So basically, you find that, if you move along the main diagonal or any other diagonal in the matrix, you find the same element. So the element is the same so long as the difference between the two indices is the same. So that's a tuplets matrix, and you need to keep it in mind because, like, it will come later on, and we will learn, if you don't already know about circulant matrices. They are very important in Fourier analysis. So matrix A is symmetric because AVK is equal to AKV. The element AKV is basically, it depends on V minus K. So basically element A21 is equal to element A32 is equal to element A43, and so on. It just depends on the difference. So the matrix is the so-called tuplets. So it's symmetric and tuplets. Okay, and it is real valued. It is real valued because, when we do this integration, see what we ended up with. Where is I? No I. So it is it's a real valued symmetric matrix. Okay, so basically the I will disappear. And then finally, if you check whether this matrix, the definiteness of the matrix, you can basically take the matrix, involve it in a quadratic form with Z Hermitian and Z Hermitian EZ, and so you take the matrix, and now it's better actually to go to this form for the matrix and multiply from both sides by an arbitrary vector in the big n dimension space, vector Z, and you compose the quadratic form, and then basically Z Hermitian, H Hermitian Z. Well, that is basically Z Hermitian H squared or H Hermitian Z squared, regardless of whether you write it like this or that. This is a magnitude squared of a complex quantity, and so this thing is real valued and non-negative. This thing is real valued and non-negative. So matrix A, so matrix X is positive semi-definite, because like for every Z in the n-dimensional space, Z Hermitian EZ is non-negative. And so basically it is a positive semi-definite matrix. But we can actually say more. Because basically Z Hermitian H is like a polynomial, right? So Z Hermitian H, basically this thing is like summation L from 0 to n minus 1, ZL, Z conjugate L, and then e to the I 2 pi f FTS to the power L. It's like a polynomial. And so basically, this thing here cannot be 0 except at a number of points equal to the degree of the polynomial. Okay, so a maximum of n zeros. In other words, basically the integrand here is 0 on a set of measure 0, unless z is the all zero vector. So if z is the all zero vector, then you get a 0, and that's it. But if z is a non-zero vector, then basically this magnitude squared cannot be 0 except on a set of measure 0. And so, from the perspective of the integral, this integral is always positive. Okay, so actually our matrix is positive definite. It's positive definite in our case here. Okay, and so it's all, the eigenvalues are strictly positive, and the matrix is invertible. Okay, so now, this matrix is very nice, very cool, and it has those properties. It's real valued, it's tuplets, it's symmetric, and it's positive definite. And its eigenvalues, because it's positive definite, its eigenvalues are basically positive, and the maximum eigenvalue is less than or equal to 1. Why? Remember actually the definition of the objective function. The definition of the objective function is what? It's a fraction, right? You take the energy between minus w, you take the energy between minus w and w, and the total energy from minus fs over 2 to fs over 2, right? So basically, from the very first step, we are talking about something that cannot be greater than 1, right? So you can basically, so this form here, this S transpose A S transpose, this is our alpha w, this is our objective function. And the objective function is a fraction, so I can write down things like 0 less than lambda n of A is less than this thing, less than or equal to lambda 1 of A, and so on. Now this matrix, it has other properties that are difficult to derive. So for example, basically the eigenvalues are distinct. Okay, so we don't have equality like this. Okay, and so these are proofs, proofs that are like that are beyond the tools that we know. Okay, but I think in one homework problem I will just tell you, take it for granted that the eigenvalues of this matrix are distinct. Okay, but at least for now, it's very clear to us why, according to the tools that we have, at least we can know that basically this matrix is positive definite with strictly positive eigenvalues, and that the maximum eigenvalue we here denoted as lambda 1, is less than or equal to 1, because basically S transpose AS over S transpose S, this Rayleigh quotient, well, it's a ratio. If from the very beginning it is a ratio that cannot be greater than 1. You write down your optimization problem like this, and that's it. That's it, right? For symmetric matrices, that basically this quadratic form, and I think like in homework one, like we solved optimization problems. Actually, we solved like even a more difficult optimization problem. Like what if you have a matrix also here? So the so-called generalized Rayleigh quotient problem. So this one, for symmetric matrices, well, this quantity here, it's lower bounded by the minimum eigenvalue. It's upper bounded by the maximum eigenvalue. It's basically one of the properties. And by the way, this is true for a real valued symmetric A, even if it's an indefinite matrix. So basically, the idea that this form here, this Rayleigh quotient, is lower bounded by the minimum eigenvalue, upper bounded by the maximum eigenvalue. Actually, it is. It is for any matrix, so it may have like a mixture of positive and negative eigenvalues. But for us here, it is positive definite. It is positive definite. But again, the idea is that now we can solve our optimization problem, because is this maximum achievable? Yes, it's achievable. How do we achieve it? Choose S to be an eigenvector of matrix A that corresponds to the maximum eigenvalue. That's the solution. Right? So if you want to derive this optimal window, this window in which most of its energy is concentrated between minus W and W, where W is a given specified parameter, basically it is, how do you get it? You construct your A matrix. Okay, so you have an A matrix. These are the elements of A. So you know Fs of your system, you know W, you know N. Okay, you construct the n by n matrix A, do eigendecomposition on A, the eigenvector correspond, basically corresponding to the maximum eigenvalue, that's the Slepian window. That's the window that basically has, most of its energy in the main lobe, and it has suppressed side lobes. Okay, and so in MATLAB, I mean, this is another name for the Slepian window, and because you can actually use this instruction to play with this window in MATLAB. Okay, we are not done yet in terms of making the Dtft practical. So the Dft to be practical, so you have the windowing business, okay, which effect, I mean, the most important thing here is like to have a finite sum, but we also have still a problem, which is that the Dtft has a continuous frequency variable. We cannot deal with an infinite number of frequencies. We need just to deal with the spectrum computed at a discrete values, a discrete set of frequencies. And so this will be the last step, basically, to go from Dtft to Dft. So we will have to sample or discretize the frequency variable.